Okay, hi everyone. Welcome to another Flan Talk this week by Michael Goodale, who's going to tell us about meta-learning neural primitives rather than Bayesian priors. Thank you.
All right, hi. So I'll be presenting indeed this paper from ACL that we presented a couple months ago, Meta-Learning Neural Primitives rather than Bayesian Priors. It's joint work with my supervisors, Salvador Mascarenas and Yair Lecretz. So this is really a sort of, in some sense, a cognitive science talk that uses neural nets and formal languages in sort of a deep way. But ultimately, the point is about how to interpret things from sort of a theoretical point of view. And so the first half of this talk, I'll be sort of summarizing some of the cognitive science background that kind of motivated the debate that the paper is trying to address. So we have a sort of maybe something slightly different than what's typically done here. So one sort of basic fact about neural networks and about humans that I'm sure many of you are very familiar with is that in general, we say that humans tend to generalize pretty well from small data. Like they tend to extrapolate, at least in ways that we normatively like, whereas neural networks don't really, right? So while LLMs seem to have performance on grammar, like in terms of grammaticality, that rivals humans, it's very similar. They have to do this with enormous data sets in a way that's very non-human, right? So like a child will have only heard maybe like 100 million sentences, 100 million words, something like this, whereas LLM to get very, very niche grammaticality judgments might need orders of magnitude more data. And so there's been some work to try to address this, such as the BabyLM workshop. But to the best of my knowledge, there hasn't been really anything that really rivals like humans' ability to learn language off of these like very small amounts of data. And so obviously there's an enormous amount of debate about why that is, right? One sort of class of accounts in cognitive science that we're kind of dialoguing with in this paper are from what's called rational analysis. So rational analysis is this sort of research program that was developed in the 90s in cognitive science that tries to look at cognitive functions in a sort of very abstract way. And so the idea is that, if you want to understand the mind and you want to understand what the mind is doing, you have to think about like the context in which the mind evolved, right? And there's sort of an assumption, which is that, you know, you should assume that cognition is some sort of optimal response to the information processing demands of the environment, right? So the environment puts all this pressure on you, you have to evolve to somehow deal with this, and we kind of make the assumption that, okay, we can assume humans are optimally evolved, right? I don't necessarily agree with everything in rational analysis, so I'm kind of vulgarizing it a bit, but that's sort of the main idea. And one takeaway of this is that in general, if you want to be evolutionary adaptive, you have to be rational, right? You can't go around doing things that are completely nonsensical, that don't have any bearing on reality, because then you're going to get eaten by a lion or starve to death or something. So you need to be rational in some sense. And then, of course, this begs the question, what is rationality? How can we define what it means to be rational in a sort of general framework that we can approach in a mathematical or formal way? And so, in general, the answer that rational analysts have sort of tended to go towards is to say that Bayesian accounts are basically the way to go, right? So, what is rationality? It means to follow Bayesian prior, right? And there's a lot of ways to a lot of reasons to assume this, right? So, like you know, it's good to have some sort of basic idea of what the world is before you go out and do things. You shouldn't just mimic the data you see perfectly. But of course, you should update your beliefs with respect to new knowledge, all these great things. And on a very like high level description, it seems like a good account of what rationality could be, right? It might not be a sufficient account, but at least captures some aspects of rationality. And it's quite popular. And now there's a whole sort of raft of cognitive accounts that really take this Bayesian approach to some extremes, right? So for that reason, people tend to think of rational analysis as being really tightly linked with Bayesianism. The question, of course, though, is what prior, right? So Bayesianism is great, but it doesn't really tell you which prior to choose. There's no sort of a priori reason, to choose any given prior over the other. And for some things, it might be obvious. So for something like visual processing, you might think that the best option would be to just sort of take what's in the environment, right? So we evolved in some context, we saw trees, we saw grass, we saw all these things. We should have a visual system that somehow reflects the facts of those environments. That seems fairly straightforward. But when we start going to higher abstract notions of cognition, it gets more difficult. right? So if you think about language or you think about reasoning, it's not clear what sort of facts in the environment that we should just blindly imitate in terms of a prior. We might need something more complicated or something more useful to sort of describe what the best priors for these higher order things. And in fact, complicated was the exact opposite of what I should have said, because a common assumption by rational analysts and many other people is that simplicity might be the best sort of prior to have, right? So with all else being equal, you should choose the simplest explanation for something or the simplest description of something, and that will give you the right kind of generalizations. That's not quite enough to build the framework, but it gets you the broad picture. And so the way you typically formalize this is with something like Kolmogorov complexity or Solmonov complexity, if you prefer, which is just basically how complicated a program you need, like in a programming language, to generate some data is. And so this has really been considered to be like the solution for our like inductive biases that drive our learning by a number of people, in particular Nick Chater and Vitania, who have really vigorously argued this. And so it's really inspired this sort of broad category of research programs in cognitive science to kind of account for what humans are doing. Now, there are all sorts of models that people have developed concretely and computationally that use this approach, right? So one that I'm going to talk about right now that will be useful for the rest of the talk is from Yang and Pantadosi's paper from 2022, which basically used this sort of Bayesian rational analyst approach to model formal language learning, right? So it's the one model for learning language. Some of you might have heard of it. And the way that it goes is, you have some sort of data, a small number of examples, like very, very small. So in this case, you have something like A, right? I think most of you here could recognize this probably would be A to the N, right? Any number of A's, that language. Of course, you might prefer another language. You might be a smartass and say, well, I only see those strings. That's the language. It's the set of those strings, right? These are all equally good if you don't have any reason to choose between them. And the technique in Yang and Pantadosi is to basically take a bunch of simple, basically design a very simple programming language that's designed for manipulating strings, and search the space of those programs to find programs that generate the data set, and then adjudicate between them according to a prior. So in this case, it's a prior for simplicity. So the idea is you try to find a program that generates this data while keeping it as small as possible. So you want to find something that's likely to generate the data that is very, very small. And so in this case, you might learn a little language like this, or a little program like this, which has a conditional, it flips a coin, and it either prints A, or else it recursively appends A over and over again. So it generates the language A to the N. And crucially, A to the N is simpler to express with the primitives than the set of just those A's, right? So it's better to assume this generalization than to assume just memorizing the finite set because of the simplicity prior, right? Otherwise, you would prefer to memorize the set per primitive. Now, why, this is all great, whatever. If this is the right research program, why do we need more, right? And the sort of practical reason that we need more is that these kind of techniques are using symbolic modeling and searching over spaces that are very, very hard to search, right? So typically use techniques like Monte Carlo Markov chains and things like this. This works well for toy models. It's fine if you're trying to illustrate a point, but if you want to do some very like complicated behavior that's very narrow, it becomes trickier, right? So it becomes very, very impractical. So for reference, training a language in Yang and Pantadosi to do something like the language of balanced parentheses, like the Dict language, I think it takes something like 7 days in their model, right? Like it's really, really impractical to train, and it's very expensive. And it would be basically impossible for anyone to do something like actual English grammar or something like this with these kinds of approaches. It's just not tractable. And so, the kind of question that a lot of people are asking and they kind of want to address is, how can we have our Bayesian cake and scale it too? Like, how do we have both of these things at the same time? Like, wouldn't that be great? Because could have a cognitive model that we could ask very like narrow questions about. And so one solution that's gone really popular in the last, 4 years has been to use meta learning, right? And so there's been a raft of a bunch of papers talking about meta learning in some ways, including a big review article in BBS, which just sort of was really like hyping the idea, which is the Binset paper. And so you have a bunch of other papers, such as the Lake and Brony paper which was in Nature, which tried to claim that they've found a model that's perfectly systematic, that behaves in a way very similar to humans, with some caveats. And finally, this McCoy and Griffiths paper, which looks at Yang and Pintadosi and similar things like it and tries to adapt it. And our paper is really a response, in some sense, to the McCoy and Griffiths paper, which I'll explain in a moment. But just to overview meta-learning, if you guys are not super familiar with it, the idea of meta-learning is it's sort of a broad category of techniques where you train a model on how to learn, right? So it's sort of like a second layer of optimization, where rather than just narrowly optimizing on a single task, you optimize on a distribution of tasks so that you can learn some specific tasks later, faster, and better. And so the idea of this whole sort of school of thought is to design an interpretable prior, right? Come up with some prior that you like, that's nice, and meta-train a neural net to sort of imbue the neural net with that prior, right? So it's like we've got this great symbolic prior. It's easy to interpret. It has nice generalizations, and we have this neural net, which is nice because it's fast to train. It's maybe closer to the brain in some sense. Uh, you know, in some sense, like there's a lot of advantages to it. So we want to sort of put the two together and combine them. So the specific kind of meta-learning that we're looking at, I'm not going to get into the technical details really because it's not super relevant, is model-agnostic meta-learning, which is a technique from Finidal in 2017. And the idea here basically is you have a distribution of tasks, and you sample from that distribution of tasks, and you get a single task that you optimize on. And so you take your model, you train it on that task, and in the end, you have some finished model. And that finished model, you then evaluate it on some held out part of the task, so a test set for the task. And you get a sense of how well the model has learned the task, right, based on that. And you use that signal to update the initial parameters of the model, so all the way before any training at all, right? And then you go down and you do it again with another task, right? So the thing that you're really optimizing is the initial parameters of the model. So it's basically a very complicated technique to learn an initialization function for a neural net. And you can do it on all sorts of tasks. And we're obviously focusing on language learning. So what McCoy and Griffiths do is they meta-train an LSTM with MAML to learn formal languages. So they create a data set of a bunch of languages sampled from an interpretable prior that they designed based off of the Yang and Piantadosi paper, where they have this, a bunch of different languages, sort of preferring simple ones, and they train the model on this. And what they find is that the model learns these formal languages much better and much faster than the unmeta-trained model. So if you look at this figure here, basically if you take the Bayesian model, so this is the model from Yang and Piantadosi, and this y-axis is the F-score, which I'll explain in a moment, but it basically, you can think of it as just like how well the model has learned some specific language. And this is over a set of test languages. They find that, the Bayesian model learns pretty quick. So by the time you have 100 training examples, it can learn most languages pretty well. And then conversely, if you take the neural network, which is uninitialized and just trained normally, it takes a long time to learn. Like it needs at least 1,000 or 10,000 examples to start getting a decent performance. Whereas their meta-trained model, or as they refer to it as the prior trained neural net, kind of mimics the Bayesian model in some sense, right? So you start learning a lot faster, you can get decent performance of only like 100 training examples. So it has some nice properties. And one interesting thing is they also applied this to English, and they found sort of mixed results, but they found that the model tended to do depth generalization a bit better. So if you evaluated it on things with grammaticality with like very deep embeddings, it did a bit better. But in general, there wasn't like a massive difference. This is obviously a bit similar to some of the work on pre-training from Michael Hu that I believe he presented here actually. So it's a bit similar, but I think it predates it a bit. And so the thing that we're kind of addressing in this paper is that there's sort of a key assumption here, theoretically, which is that the models are doing better because they've acquired the prior, right? So they always describe this model as, being imbued with a prior, being distilled with a prior, they call it the prior trained neural network. And so what we're really interested in asking is like, is the model actually acquiring a prior in any substance or a desired prior in any substantive sense? So, like what exactly is the model getting at the end of this? And so we come up with sort of two hypotheses that we contrast in our paper. So the first is this sort of simplicity bias view that we call, which is basically what I've just been describing. The model acquires a prior because it's been meta-trained, it's been optimized to sort of follow that distribution. And the reason the model works is because it has the simplicity prior that was given to it from the data set. Like the data set has a simplicity prior, the model will now make generalizations that in some sense approximate the simplest solution where it didn't previously. And so that's why the model is doing better. Our alternative view is maybe a bit more reductionist, is we call it like mechanistic complexity. And we say that the meta learning works just because the model is sort of learning useful neural mechanisms, right? So the idea is that the model, in learning all of these different languages over the course of meta training, it comes up with, I like to think of it as like a toolbox, right? So it has in its weight space a bunch of little like things that it can then repurpose for different languages, which allows it to learn things relatively quickly, right? So it has this, a little mechanism that does one thing, maybe it counts how many of a specific character, and that's useful in a bunch of languages, or it does some other more exotic thing. So these are the kind of two views that we're going to contrast. And so this is this nice figure I made for the poster that I just have to show off. But we have this sort of basic problem. Meta training takes something that requires a lot of data to do something kind of mediocrely to having a small amount of data and doing quite well. And really, is it the model getting a prior? Are you sticking a prior into a neural net? Can you think of it that way? Can you then use it as an approximation of a model that you've written out symbolically? Or is the model just sort of learning, little like tools, as I described previously? So to test this, we came up with two data sets or two sets of data sets that handle it differently. So the first group are sort of informationally complex data sets. So these are data sets that we use to test the simplicity bias view. And to do this, we sampled 5,000 different languages from a formalism. Specifically, I used the minimalist grammar formalism from Ed Stabler, not for any sort of deep reason, just because I've been using it a lot recently, and so I was familiar with it. It has some nice properties. It's context sensitive. It's reasonably expressive. Um, and so what we do is we sample a bunch of languages from this formalism, varying in complexity. So to measure the complexity, we basically just keep track of how long the grammar is, essentially. So it's just like how many bits do you need to encode the grammar? And we come up with a data set of 5,000 languages that are equally distributed across a range from 0 to 100, right? I'll show you some of the grammars later to get you a sense of like how complicated these are. But so then we can then manipulate this data set to come up with different priors. So we have a uniform distribution. We have a distribution that strongly prefers simple grammars, right? So you're going to see a lot of very, very simple languages over and over again. And then we can have a distribution that sees a lot of very, very complicated grammars. The temperature here is just describing how we generated the distributions. It's just a softmax over the complexity. So it allows you to sort of weight it in one sense or the other. And so we train 5 different models on these different data sets, and we try to see if they behave differently. To give you a sense of the grammars, so if this is a very simple grammar, this one has like an MDL of like 7. So it's like model description length is very short. As you can see, there's not a lot going on. And all of our strings, we just use numbers instead of anything else, just because it's the simplest thing to represent. And so this grammar is obviously A to the N. It's very simple, very straightforward. Once you get sort of the middle of the road, something like 52, the grammar starts being a bit harder to characterize so straightforwardly. So you have a lot of different characters, but there's some patterns that are pretty easy to pick up, such as where the fours can go. You can't see it here, unfortunately, but if you are to embed the sentence very long, every time you need to use a 6 to basically embed something longer. It's the only way to make a longer string is to put a 6 in front of it. So you get these sort of simple patterns that are reasonably complicated, but not like crazy. And then finally, if you get to like a very, very high complexity, you have something like this, which I won't even really try to characterize, but it involves like complicated dependencies and movement and weird stuff. There might be a simpler description of it, but it is very complicated. So you have this kind of real range of different languages. So that's the one thing that we do to test the simple languages. So we come up with this data set sort of family. For the mechanistically complex languages, we do something very, very different. So we train just on a single language. So there's no sort of distribution. Um, the model just is always seeing the same language over and over and over again over the course of meta training. Um, because this is something that we should expect to happen under the mechanistic view because you just need to learn these little techniques, right? You don't need necessarily to see a bunch of diverse data. You just need something that gives you a reason to learn some particular tool or mechanism or circuit or whatever you want to call it. And so we chose 9 different languages to make our data sets, sort of varying into 3 categories based on basically family resemblance, and then stratified according to their position on the Chomsky hierarchy. In retrospect, we probably would have been better to choose a different kind of complexity measure, but this was available to us and simple. And so some languages A to the N again, A and BN, and A and BNCN, right? So sort of increasing in complexity. The second class of languages we used were a very kind of dumb language, the Kleene star language. So it's just any numbers of any sort of string of the valid characters. And then this script's expanded into 2 variants. So one where you have the string and then it's repeated, but mirrored, which is the sort of context-free and relatively simple. And then a copying one where you copy the string twice. So context-sensitive instead. And finally, we do a bunch of languages based off sort of the tick language. So one, it's just ABN. So it's just sort of, opening, closing over and over again. And then the standard sort of Dyke language, where you open and close, but you have brackets and you can arrange the parentheses in any way. And finally, a context-sensitive version where the brackets and parentheses can be interleaved, right? So they don't depend on each other. So the ordering of the two doesn't matter. In some sense, it's actually, despite being context-sensitive, in some sense, it's also simpler. And so the model that we do all of this on is we just copy the hyperparameters from McCoy and Griffiths. So it's a 1,000-dimensional LSTM. We train, I think, on I think there's like 25,000 presentations of the languages. Now, the one sort of trick that we do for the mechanistic one that's I think quite relevant is the tokens are shuffled over the course of meta learning, right? And so the reason we do this is because if the model is just seeing truly the exact same language every time, there's not really any sort of meta learning that it has to do. It's just regular learning, sort of straightforwardly. And so what we do is every time the token assignments are changed. So this has 2 benefits. One, the model has to learn something rapidly every time. It has to learn to adapt. And secondly, it allows, on a more simple note, is it allows us to initialize all of the word embeddings. Like all the token embeddings get initialized, even if the language doesn't have many characters, because ultimately they'll all get used over the course of the meta training. And in some sense, it's quite nice because then later on, if we apply this to English or something, you can have a much larger vocabulary. And the evaluation is this sort of custom metric that's a bit complicated that I'm going to explain because I think it's pretty useful, which is based on how to continue a prefix string rather than what McCoy and Griffiths and Yang and Pintos used. So both of these papers use something that they call an F1 score. It's not exactly an F1 score. It's very, very similar to evaluate their models. And this is sort of their measure of how well a language has been learned by the model. The technique is to basically, you come with the precision. And what they do is they sample a bunch of strings from the grammar according to their like gold grammar or whatever sort of model they're using to generate, come with a big corpus of strings. And then they have their model and they generate a big corpus of strings. And they compare these sets. And so the way they compare the sets is that if the top 25 most likely strings in the model's corpus are in the target language, then that would be that's the degree of precision. It's just how many of the top 25 of the model strings are in the target corpus. Conversely, the recall is just the other way around. So you take your gold grammar, you take the top 25 most strings, and you see how many of them are generated by the model. Now, the problem with this, of course, is that that's not how formal languages work, right? The top 25 strings is not all you need. You need a lot more. And also on a more deeper level, besides just this hyperparameter that's kind of arbitrary, it assumes that formal languages are ordered, right? So it makes this assumption that some strings are more emblematic or more frequent than others, which you can do that, you can choose to do it, it's fine, but it's something you're adding to the formal language. It's not something intrinsic in the formal language. And so maybe makes sense from a sort of Bayesian perspective, but it's a bit complicated if you're interested more in just how expressive the model is and things like this. So what we do is we do a technique which isn't based off sampling, but it's just based off of the next tokens that the model makes. So it can apply to any sort of technique that generates the next token. In fact, it wouldn't actually work for Yang Pantanussi's model because it doesn't function this way, but it works for neural nets. So the technique is basically we keep the F1 score, keep the idea, but we base it on just the next tokens that are going to be generated by the model. So in this case, what we do is we take some set of strings, like a big corpus, and we come up with all of the prefix strings that you can make of that corpus. And then at every step, we take the model and we see what it outputs as or like what's the distribution of next tokens. And we have a set of tokens that are good, that could lead to a grammatical sentences, and a set of tokens which are bad, which could not lead to a grammatical sentence. So in the Dyke language here, you can see that if you have an open parenthesis, you can open another parenthesis, you can open a brace, you can do any of these things, or you can close the open parenthesis, but you can't stop, right? Conversely, if you've closed, you can stop, you can open one or not. It's pretty straightforward. Now, the precision analogy we use is to just take the probability mass of all of the correct valid tokens. So it's just like how likely it is are you going to be to sample, how likely is it that you're going to sample one of these tokens? And that gives you a sense of how precise the model is. The problem with this is it's definitely not sufficient as a measure because you could have a very stupid model that just always chose the open parenthesis, for example, and that would be 100% precise, but it has not learned the language in any substantive sense at all. So we have this more complicated metric that we call call. I think of it as like better than is what I refer to it to. And it basically just looks at all the valid continuations and it counts the proportion of them such that that token is more likely than all of the bad tokens, right? So if you have the set of bad tokens, even if this closing bracket is really, 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 really unlikely, it should always be more unlikely than anything that is completely syntactically invalid, right? So it allows you to have a model that maybe really, really likes some family of strings. As long as it knows that other strings are better than all the bad ones, we count it as having learned the language in some sense. But it only works over a corpus, right? You have to define some set. And it has some other nice properties, like you can look at length generalization and things like that with it. So to sort of sum up what we've talked about so far, we have these two views, simplicity bias view and the mechanistic complexity view. And in the simplicity bias view, we've evaluated it with sort of 5,000 languages that are distributed in different ways to either favor complexity or simplicity, right? And we want to see, is the neural net, getting this prior? Is it acting in that way? And the sort of prediction under this view, if the model is acquiring a prior, and if simplicity is like a useful prior, you should expect basically the model that sees a lot of some simple languages proportionally to do quite well and to improve a lot over the unmeta-trained one. Whereas a model that's just sort of seen like a uniform distribution or not really might perform slightly worse. Like it still learned something about language learning, it's still somewhat useful, but it's maybe not enough to get like the right exact prior. And one interesting thing is you should maybe predict that a preference for complexity should lead you to prefer very like bad generalizations because you're going to assume kind of crazy things instead of simple things. So you'd actually perform worse than the unmeta-trained model. Conversely, under the mechanistic view, we're claiming that the model is just sort of learning these mechanisms that it can repurpose. It doesn't really matter if it's seen a diverse set of data. All it matters is it's seen data that's incentivized it to learn some sort of mechanism. So these are data sets with a single language. And we kind of make the prediction that maybe you should perform differently depending on how complex the language is. So if you see a language that's very dumb, like the regular language, the Pliny star language, which is not very, it doesn't have anything useful. You're just sort of randomly guessing at every step. It might help you a little bit, but it's not going to help you very much. At best, you might learn a distribution over sort of how long strings can be, or a preference to stop. Whereas if you have a language that's more complicated, you might have to learn something complicated to express it. And once you have this complicated mechanism, it'll be useful for something else. And so, at long last, we have some results. And so, oops. Oh, there we go. Oops, jeez. So these are the two figures. This is really the big figure of the paper. And what we find is that we find evidence for the mechanistic view. So if you look at the simplicity languages, so the languages that are varied in how complex they pretty much all perform about as well as each other, right? There's some slight differences. So if you see the complex languages actually do slightly better than the simple ones, which wouldn't really be predicted by that view. But the ordering is not like monotonic between the different groups. So you'll see that being strongly simple seems better to be slightly simple and things like this. So we suspect this is largely just noise, the ordering. It might not be, but there's and there's a decent improvement over the unmeta-trained one, but not quite so dramatic. One thing to note as well is that our figures look very different from McCoy and Griffiths, largely because we're using this different, more sensitive metric. Now, conversely, under the mechanistic view, we see something very, very different. So there's very clear distinction between the regular languages and the context-free and context-sensitive languages. So these ones, the ones that are more complicated, have led the model maybe to learn something useful that it can repurpose. And what's really interesting is that, in fact, the context-free and context-sensitive languages actually perform better than any of the informationally complex ones. And this is despite the fact they've only seen one language over and over again. So, we have this sort of surprising thing, which is, first of all, preferring simple or complex languages, shows no real difference in model performance. And that meta-training on a single mechanistically complex language can help more than meta-training on many, many, many mechanistically simple languages. So if you have to basically choose the languages very carefully. And so there's sort of a natural question that comes out of this, which is sort of like what languages are easy to learn? Like what is the model, what has the LSTM been learning? And what we sort of suspect, we haven't done we haven't really looked into the models directly, is that the models are basically learning, these very simple mechanisms that we've seen already in LSTMs. So if you look at Weiss et al. In 2018, they found that LSTMs learn sort of simple counting mechanisms. And so this figure from their paper, you can see that, in the lane space, there's this very clear counter that, as the string goes on, you get to 1,000, you've counted to 1,000, and that's how you know how to recognize a language. And so this allows them to learn some languages like A and B and C N very well, but then others like the copy language remain difficult. So this is why I said earlier that we use the Chomsky hierarchy, and in retrospect, it probably would have been better to choose a different ranking, but we still found what we were looking for. Now,
Which
yes.
languages did you try?
Like
What?
did we evaluate
Yeah,
on?
yeah, yeah.
We evaluated on the same 9 languages I described,
Okay,
holding out the if a language was trained on one, we held that one out, right? So the A and B and CN language didn't get evaluated on A and B and CN, obviously. Yeah, those are the 9 languages. Sorry, yeah, I should have put that in the slide. Now, the last thing to sort of talk about here is that transformers can't sort of easily express counters, at least from what I understand. And this kind of follows from what McCoy and Griffiths found, which is that they have this sort of footnote where they say, look, we tried transformers, didn't seem to work too well with what we were doing, so we stuck with LSTMs. And they don't really go into it in very much detail, but I think there's a pretty straightforward explanation, which is just that LSTMs have a better expressivity of the kind of class of things that they were trying to learn. Now, there's an interesting thing, which is, GRUs can't count. So this is something that Weissel pointed out. If you look at the figure, GRUs learn these crazy, wacky things instead of a nice counter. So they don't really have the expressivity. And so last thing we did is we just completely repeated the meta training on GRUs. And so you should expect under the prior view that meta training will still give you some advantage, even if you're not learning the counter or something, right? Because you learn, something about the distribution, you kind of imitate it in some sense, it'll put you in a nicer starting position. But we didn't find this. No, we found that GRUs don't show the same meta learning effect. And probably because they can't express counters, they don't learn any useful neural mechanisms over the meta training, and they perform as well or worse than the unmeta-trained model. So in this figure, you can see the hatch lines with the GRUs, and once they've been meta-trained, they actually perform worse than when they were unmeta-trained, which is unlike the LSTMs. And this is pretty hard to account for under the prior view, right? Like the prior-based view, because why should it be that GRUs do worse, other than the fact that they can't express things as well? So to sort of put away to do some takeaways, there's not really any evidence that MAML imbues models with the specific prior that's found in the data set. So you might want to describe this at a very, very high level as the model learning a prior. But from a theoretical point of view in cognitive science, the goal was really to take a specific prior and put it in a neural network. And this doesn't seem to be what's happening in meta-training in any substantive sense. So models don't really narrowly copy the prior that they're trained on. So unlike sort of standard training where the model approximates the distribution in some sense, there's no guarantee that the meta-learning is going to approximate the distribution in the same sense, right? Because for example, these languages were trained on, or sorry, these models were trained on one language. So you should expect the prior to basically be a point, right? They should do that one language really well and everything else a bit poorly. But this is not what we find at all. So meta-training can, on a single language, can help you as much as meta-training on 5,000, provided you choose the right language. And so our sort of interpretation of this is MAML imbues models with mechanisms that are useful for similar tasks rather than neural priors. And with that, I'm done. So thanks.
Cool presentation. A query that